One of the biggest misconceptions in modern genetic genealogy is that if two people share a DNA segment, we automatically know which ancestor it came from. That simply isn't true. Every day, people claim that a particular chromosome segment came from Pocahontas, a Cherokee ancestor, a Viking, or another famous individual because they found a DNA match. Unfortunately, DNA doesn't work that way. A chromosome segment has no label attached to it saying, "I came from John Baird," or "I came from Pocahontas." Our job as researchers is to determine the most likely origin of that segment using evidence. Today, I'm going to walk you through the methodology professional chromosome mapping project should follow. We'll discuss why documentation matters, why triangulation matters, why identifying the most recent common ancestor is essential, and why lowering centimorgan thresholds before establishing a solid foundation can easily lead researchers down the wrong path. By the end of this presentation, you'll understand that chromosome mapping is not guesswork. It is a scientific process that builds layer upon layer of evidence until a chromosome segment can be assigned with reasonable confidence. The first rule of chromosome mapping is simple. DNA does not replace genealogy. Many researchers approach DNA as though it can magically tell them who their ancestors were. It cannot. DNA can only test a genealogical hypothesis. If your documentary research is weak, then your DNA conclusions will also be weak. Before we ever open a chromosome browser, we should already have spent considerable time building a documented family tree. This includes birth records, marriage records, probate records, land deeds, tax records, church records, military records, census records, newspaper articles, family Bibles, and any other records that help establish relationships. The stronger your genealogy, the stronger your DNA interpretation becomes. Think of genealogy as building the foundation of a house. DNA doesn't replace the foundation. DNA helps verify whether the house was built correctly. Once we have documented genealogies, our next goal is identifying what genetic genealogists call the most recent common ancestor, or MRCA. This simply means the closest ancestral couple shared by every individual participating in a study. Notice that I said ancestral couple, not simply an individual ancestor. Most chromosome studies identify DNA inherited from couples because we usually cannot determine which parent contributed the segment several generations back. Suppose 4 different testers all descend from William and Mary Johnson through completely different children. William and Mary become our working hypothesis. Everything we do from this point forward attempts to answer one question. Did this chromosome segment originate from William and Mary Johnson? That hypothesis must be tested. It is never assumed. This is one of the most overlooked concepts in chromosome mapping. Many researchers identify one cousin who shares DNA and immediately declare success. Unfortunately, that's not enough. What we want are descendants from multiple independent branches of the family. Imagine 4 children of the same ancestral couple. Now imagine descendants from each child all carrying the same chromosome segment. Suddenly, we have something much stronger. Each independent descendant line acts almost like another witness in a courtroom. One witness may be mistaken. 5 witnesses telling the same story become much more convincing. This is why larger chromosome projects become increasingly reliable as more descendants participate. Each additional independent branch either strengthens or weakens the original hypothesis. Chromosome mapping depends entirely on accurate genealogy. If one relationship in a pedigree is incorrect, everything above that individual becomes questionable. This is why experienced genealogists spend enormous amounts of time documenting every generation. No family tree is ever perfect. There will always be gaps. However, we should strive to support every relationship using the best available historical evidence. Sometimes that evidence comes from direct records. Other times it comes from indirect evidence assembled into a convincing proof argument. Regardless of the method, documentation should always precede DNA interpretation. DNA confirms genealogy. It should never replace genealogy. Now we arrive at triangulation. This word is often misunderstood. Triangulation is not simply 3 people matching one another. It requires 3 conditions. First, person A matches person B. Second, person B matches person C. Third, person A matches person C. Finally, and this is the critical requirement, they must all overlap on the exact same chromosome segment. Without that overlap, they are not triangulated. Triangulation tells us these individuals most likely inherited the same piece of DNA from the same ancestral source. Notice I said most likely. Science always leaves room for alternative explanations until enough evidence has accumulated. One mistake I frequently see is researchers starting with tiny DNA matches: 5 centimorgans, 6 centimorgans, 7 centimorgans. Small segments can absolutely be useful, but they should never become the starting point. Instead, begin with larger chromosome segments. Larger segments are much less likely to represent random identical bistate matching. They generally provide stronger evidence of recent shared ancestry. By beginning with stronger evidence, we establish a reliable chromosome map. Only after that map exists should we begin exploring smaller segments. Think of it like constructing a building. You don't start with the roof, you begin with the foundation. Notice how every previous step builds toward this moment. By now, we have documented genealogy. We have identified our MRCA. We have collected descendants from multiple independent branches. We have triangulated chromosome segments. Only now do we begin assigning chromosome segments to ancestral couples. Notice the order? We did not begin by assigning DNA. We earn the assignment through evidence. This distinction is extremely important. Science requires skepticism. Before assigning any chromosome segment, we should actively attempt to disprove our own hypothesis. Could these testers be related another way? Do they descend from multiple colonial families? Could endogamy explain the match? Could pedigree collapse create the appearance of shared ancestry? If another reasonable explanation exists, it must be investigated. The strongest chromosome assignments survive attempts to prove them wrong. Now we finally arrive at smaller chromosome segments. Notice how long it took us to get here. That was intentional? Imagine we have already identified a chromosome segment between 180 and 197 megabases on chromosome 3. And in the case of my Anne of the Potomac study, this is what actually occurred. Dozens of documented descendants from multiple independent lines triangulate on that region. Only now does a new 6 centimorgan match become meaningful. By itself, 6 centimorgans proves very little. Inside an already documented chromosome map, however, it becomes supporting evidence. The map provides the context. Without the map, the small segment is little more than a hypothesis. Small DNA segments are often misunderstood. Some are inherited from genuine common ancestors. Others occur purely by chance. Some may even represent very ancient ancestry that cannot realistically be assigned to a single documented ancestor. This doesn't make them worthless. It simply changes how we use them. Small segments generate hypotheses. They suggest new research directions. They may reinforce already established chromosome assignments. What they should never do is serve as the entire basis for an extraordinary genealogical claim. Let's review some of the most common mistakes I encounter in genetic genealogy. The first is assigning DNA to an ancestor before triangulation has even occurred. The second is relying on only one descendant line. Third is neglecting documentary evidence altogether. Fourth is failing to recognize endogamy or pedigree collapse, both of which can create misleading patterns. Fifth is beginning with tiny chromosome segments before establishing a reliable chromosome map. Finally, perhaps the most dangerous mistake of all is confirmation bias. Researchers often become emotionally attached to an exciting theory and begin interpreting every new DNA match as evidence supporting it. A scientific researcher does the opposite. They actively search for evidence that could prove their own theory wrong. If the hypothesis survives that process, confidence naturally increases. Everything we've discussed today follows the scientific method. We begin by making observations. We develop a hypothesis. We collect documentary evidence. We compare DNA. We triangulate chromosome segments. We validate our conclusions using multiple independent descendant lines. Then we repeat the process again and again with additional testers. Over time, the chromosome map becomes stronger because every new participant either supports the hypothesis or forces us to revise it. That is exactly how science should work. Chromosome mapping is one of the most powerful tools available to genetic genealogists, but only when it's done carefully. Every chromosome assignment should rest on multiple layers of evidence: sound documentary research, well-established pedigrees, multiple independent descendant lines, proper triangulation, and thoughtful consideration of alternative explanations. When those pieces come together, we can begin assigning chromosome segments to ancestral couples with increasing confidence. Only then should we explore smaller segments to refine what we've already established. If we reverse that process, starting with small segments and building theories around them, we risk creating conclusions based on coincidence rather than inheritance. The goal of genetic genealogy is not to prove what we hope is true. The goal is to follow the evidence wherever it leads. When we allow documentation and DNA to work together in a structured, scientific way, chromosome mapping becomes far more than a collection of shared segments. It becomes a reproducible method for reconstructing the inheritance of our ancestors across generations.